Okay, welcome back. So if you recall, in the last lecture we were discussing about a compound semiconductor and heterojunctions. I have given you a brief introduction about heterojunctions and the importance of epitaxy lattice mismatch. I told you about the different kinds of compound semiconductors in group 3,5 oxides, nitrides and so on. Every time we connect to the internet and so many other areas that compound semiconductors are widely used. Okay, so there are a lot of devices to learn about that. We'll keep things simple though. Today we shall be starting with some band diagrams. If you recall, we have studied band diagrams of Schottky junction, PN junction, right, MOSFET, BJTs and so on. So what about all those structures were essentially of the same semiconductor, say silicon. But if we take heterojunctions, which means we have dissimilar materials with different band gaps, band alignments and electron affinities, then how do you form a heterojunction between a wide band gap and a narrow band gap semiconductor, for example. A PN junction made of heterojunction, all these things we'll study so that we can draw the band diagrams to understand the devices like lasers, LEDs, transistors and many other kinds of transistors and so on. There are fascinating amount of physics that can be done. I had told you that a particle in a box that you might have studied in your high school or 10+2 can be practically realized in a quantum well, where a narrow band gap semiconductor is sandwiched between two wide band gap semiconductors. So that such kind of things are possible with heterojunctions, and we should never forget that we cannot arbitrarily stack materials on top of each other. There has to be a material science permissibility, the material science has to allow that. So the epitaxy and lattice mismatch are very important. So there are many aspects pertaining to it which we have covered. So today we shall start from the types of heterojunctions and how to draw band diagrams of heterojunctions. Okay, so we'll come to the whiteboard here. So I told you that heterojunctions are essentially the junction between two dissimilar materials. Typically to have them grow on top of each other, we need to have them of the same family. So for example, you can have a heterostructure of aluminum gallium arsenide on top of say indium aluminum arsenide, for example, because they are of the same family. But you cannot have a material of gallium nitride, for example, on say indium antimonide randomly. Okay, you will not be able to get crystalline material. You please remember that these materials have to grow crystalline in order to preserve the band structure and the band diagram. Okay, so you cannot arbitrarily grow one material on top of another. It has to be permitted by the material science behind it. Okay, so those are the things we have studied. So now there are three types of heterojunctions, practically speaking. You see the electron affinity rule makes up that. So every material, so if this is the vacuum level, you have a conduction band EC, then you have a valence band EV. Suppose this is mildly n-type dope. Now the question is, in any type of PN junction or any other junction that you have studied till now, the material has always been the same, silicon, and the band gap always has been the same mostly. Okay, but if the band gaps are different, okay, for example, I might have this is the vacuum level, right? So this is the vacuum level. So let me use another color for the vacuum level. Maybe I'll use blue. So this is your vacuum level, right? And now there's another semiconductor whose conduction band might lie here, and it's a narrow band gap semiconductor. So valence band might lie here, and it might be mildly n-type dope or mildly p-type dope. Let's not use the word doping as of now. Let's assume that they are, we don't care about the doping. You see, the case is here. This is one kind of arrangement where you can have the conduction band of one side on above the conduction band on the other side, because the electron affinity of this is lower. Okay, so a junction that might be formed between them, right? A junction that might be formed between them could be something like let me use the black color maybe here. The junction might be, I'm not drawing a heterojunction as of now because there will be band bending and other things, but this could be the structure, right? This could be structure, right? That could be a structure here, but this is only one possibility. It also could have been happened that the narrow band gap semiconductor would have had a different electron affinity. For example, the narrow band gap semiconductor would have this kind of EC and EV, this kind of electron affinity where it's larger, and this kind of an arrangement in which your band diagram would have looked something like this. Okay, that's also possible. This is a different band diagram alignment. This is called different band alignment from what I had drawn in it previously. Or it could also have happened that your narrow band gap semiconductor is such that it's very narrow, and your EC is here, also the EV is here, EV is also here. So then in that case you would have had something like this and then this. So there are different kinds of alignments. So there are primarily three kinds of three types of heterojunctions are typically there. Okay, three kinds of heterojunctions are there which can be formed based on their band alignment and their electron affinity. So you have what is called type 1, and you have something called type 2, and then you have something called type 3. These are three types of heterojunction. So in the first type of heterojunction, you have a heterojunction like this. I mean, I'm not very good at drawing here, but actually this is a narrow band gap. You see, this is a narrow band gap semiconductor, right? And this is a wide band gap semiconductor, right? That's possible. So this kind of alignment is there, and this is called type 1 alignment, or it's also called straddling. It's called a straddling band alignment, not bang, it's a band. Okay, straddling band alignment. Okay, this is called type 1. Okay, this is called type 1. This type of alignment is called type 1 alignment. Then we have type 2. What is type 2? In type 2 you will have something called staggered. So you will have something like this, and then you will have something like this probably. Okay, you see the here, you know, you have a step in the conduction band coming down, the valence band also has a step here, here also you have a step, but your band is such that the second layer, the second material, okay, the second material's electron affinity is little higher, so that you know you have a step like this, but the valence band also steps down. So in a way you have a band that is aligning here. This depends on electron affinity, by the way, nothing to do otherwise. So it depends on electron affinity band gap. This is called type 2, and this is called staggered band gap or staggered band alignment. Okay, staggered alignment, it's called staggered alignment, and you can see that but this is not how in a real dope semiconductor you will have depletion and other things which I have not shown here, but I will show that. And the third one is the type 3, and this is broken gap. So you will have something like this, and as I told you, something like this maybe. These two bands are two band gaps, you know, this is band gap 1 and this is band gap 2. They are completely now like not aligned in a way, so when you join them together you form something like that. This is also called broken gap alignment. It's called broken gap alignment, or also you can call type 3. So these are the three types of heterojunctions that are possible, depends on what you are looking at. So if we do simple, you know, band diagrams, because for making any devices we should be able to draw heterojunction band diagram, and heterojunction band diagrams, if you understand heterojunction band diagrams, then you can understand actually any types of devices, semiconductor devices, including homojunction and heterojunction. But many of the textbooks and many of the, you know, the courses do not focus or do not teach the band diagrams of heterojunctions very well. So we'll make sure that here you basically understand everything. So you know, let's consider a very simple one. Suppose I have a vacuum level here. Okay, please pay attention, you will see that it's very easy to draw. Suppose I have the vacuum level here, and then I have a wide band gap material here. Wide band gap material here, I'll call it EC, EV, and wide band gap I'll use capital letter, and for small band gap I'll use small letter. Okay, this is mildly n-type dope. This is the Fermi level on the wide band gap side. So I call this is n-type, and I'll use capital N for wide band gap. On the other side I have a narrow band gap semiconductor. Suppose this is the type 2 sort of a type 1 sort of an alignment, straddling sort of an alignment. So I have a narrow band gap which is EC for example, and then I have EV, and this is mildly this is EF1, this is EF2, this is mildly p type dope, that is mildly n type dope. You can see that the electron affinity here the electron affinity here QX2 is actually more than the electron affinity here, which is QX1. That's why this alignment has happened. Now the moment you join them, what will happen is that, please remember that because they are mildly doped, you will have at the junction you will have some depletion here. Okay, because the bands will try to bend and the Fermi level has to align in equilibrium, and there will be some depletion here because the Fermi level, because your Fermi level has to align, right? Your Fermi level that you know from your other basics, Fermi levels have to align in equilibrium, they cannot have a change in position. The Fermi levels have to align, so the bands will bend to make the Fermi level align. What's happening is that, practically speaking, what is happening is that electrons and holes are flowing from one material to the other material. Electrons are flowing from the left side wide band gap material to the right side narrow band gap material, and holes that are here in the narrow band gap right material on the right side, holes are trying to move to the the left side where the holes are not or are in minority, right. So this is n-type semiconductor and this is small p, I'll give as p-type material. This is a wide band gap and a narrow band gap p-type, n band gap and n and p-type heterojunction. The depletion will form, p-n junction will form just like what we have studied earlier for silicon, except that there will be some band discontinuities here because your band gap is not the same. So the way you draw it essentially is that, and this is the most important part, this part will have, okay, so let me draw it completely here. So you have this right, this. So you see this part will essentially deplete now because electrons will go from this side to that side. So that part will slightly deplete and holes will come from here to here. So this part will also deplete as the holes will come. So essentially when I say depletion, what I mean? When I say depletion, I mean that your Fermi level, your Fermi level position, your Fermi level and the electron the conduction band edge, that spacing will basically increase if the electrons are coming from here to here and depleting, right. Similarly, the spacing, the gap between Fermi level and the valence band on this side also has to increase because holes are coming from the right to the left, and so it's getting depleted. So essentially your Fermi level and the valence band edge also have to, I mean the spacing also has to increase, but far away from the junction the spacing between the Fermi level and the valence band will not change, and far away from the junction the valence conduction band and the Fermi level here on the n side also will not change, just like in a p-n junction in silicon. Only around this point and this point your bands will bend. Okay, your bands will bend in order to form a p-n junction. So and the Fermi level has to align. So let me rub it off again so that you can basically get an idea what I am talking about here. So before joining, okay, so before joining what will happen is that I have this I have this conduction band, right. It will not be bent, of course it will be straight line. So I have this conduction band here, it's mildly doped, so Fermi level is here, and then I have the valence band here. On the other side I have the conduction band here, the valence band here, and the mildly doped, so the p-type Fermi level EF2 is also here, this is EF1. So at the junction what will happen is that you draw a, okay, it's actually too long here, yeah. So at the junction you will have depletion now, right, that's what you know. So the bands will bend, the Fermi level has to align, okay. So the Fermi level has to align, so essentially this whole thing will try to come down and this whole thing will try to go up so that the Fermi levels will align, making sure that far away from the junction this EC minus EF, this EF minus EV will be constant, okay. So what you do is that, one thing is that you see this point corresponds to this point here, the conduction band where it is meeting this interface, you fix this point in your mind, and this conduction band on the other side is fixed this point in the mind, okay. Now with that being in mind you have to bend the band. So this conduction band over here, essentially you fix this point and now you bend it, okay, it has to bend like this, okay. But far away from the junction your Fermi level has to align. That means far away from the junction, okay, far away from the junction EC and EF, this spacing has to be constant, but you are imagining that this point you are fixing the band and you are pulling the band down here so that Fermi level will align. Similarly you fix this point here, right, in your mind, and you pull this valence band up, so that it's something like this. This is the valence band, so I will have to remove this valence band here now, right. Okay, this is the valence band, this point is the fixed point where the valence band was supposed to meet the junction, okay, and this was the point where the conduction band was supposed to meet the junction. So it will also bend, the band gap has to remain same on the right side, that is the narrow band gap, this point, this has to remain same, right. Similarly on the left side the band gap has to remain same, right, the band gap has to remain same. This was the point where the valence band on the left side was there, and it has to go like this because this band gap will remain the same, okay, no questions about that. And the Fermi level of course has to align, so far away from the junction this gap has to be same, this gap has to be same, so the Fermi level is aligning here. You see far away from the junction this gap has to be same, the p type, right, and far away from the junction this gap has to be same, the n type, right. Only at the junction you see the Fermi level and the valence band conduction band spacing has increased, that means there is a depletion. Similarly Fermi level and the valence band distance has increased, that means there is a depletion near the junction. So on both sides there are appropriate depletions that have formed, okay. So please keep that in mind. And what will happen is now that you will have to join these 2 points like that, okay, and then you have to join these points to like that, okay. you have to join these 2 points like that. So, your band diagram looks like this. Okay. Your band diagram essentially looks like that. So, you have this Fermi level, right, you have this Fermi level and you have this band bending, this is EC, this is EV, this is your common Fermi level everywhere now. This is EC on the left side, this is EV on the left side, this is a wide bandgap material, it is a narrow bandgap material. So, this is your p-n junction that has formed. Okay. This is your p-n junction that has formed. So, remember here, if the band gap on this side is suppose I am just saying 3 electron volt and the band gap on this side is suppose 2 electron volt, then the difference of the band gap is called the band gap difference, delta Eg, that will be 1 volt, right, 1 electron volt. So, essentially that delta Eg essentially is the band gap on the bigger side here minus the band gap on the lower side small p. Okay. So, that is what is happening, and this point, this gap, that this straight that is formed is actually delta Ec and this is called delta Ev. These are called band discontinuities, This is called conduction band discontinuity, okay, and this is called valence band discontinuity. Okay. And you can see that there's a band bending here that has happened. This band bending that has happened, and that there's a band bending that is happened also here. This is the same as this band bending. This band bending is happening, which is the same as this. This band bending that is happening, which is same as this. So, this band bending essentially, again, if this band bending I will call it as phi n, then phi n will essentially be Q, the doping that is on this side, which is Nd, and the depletion, which is like say W n, W capital N, W capital N square by 2 epsilon naught epsilon n, because the dielectric constant on this side could be epsilon n, dielectric constant on this side could be epsilon small p, and the dielectric constants could be different. So, you remember the electric field has to be continuous everywhere. Actually, it is the electric field times dielectric constant that has to be constant, which is the displacement vector in a way you can say. So, this is the band bending on this side, and the band bending on this side, this quantity is actually phi of small p, that is given by Q n A, that is the doping on this side, times W, this is the depletion, for example, W small p. So, W small p square by 2 epsilon naught epsilon small p. Okay. So, that is the band bending that has happened on both sides, and the built in potential and other things actually you cannot you cannot just like that use the existing p-n equation, diode equation, to come up with the built in potential, because you see the depletion approximation may not always hold true in a heterojunction. You will see in very special cases that in a heterojunction you may not have depletion at the edge. I will show you some examples pertaining to that, and also remember that if one side is very highly doped, then that of course the same thing happens, the depletion side will predominantly be on the other side. Okay. Even in a heterojunction, the band bending will not happen on one side, essentially it will be only on the lightly doped side, right. So, the built in potential here, the built in potential, the built in voltage that we have studied in our classic p-n junction also, is actually the total band bending, okay, on both sides, the total band bending on both sides. So, in a way this is actually this plus this is the total built in potential, okay, is the total built in potential. You can see that you can actually derive that, by starting from the Fermi level here. You can do this, or you can also do it by other ways, and that is I will tell you. So, you start from the Fermi level here, you go up this quantity, which is EF minus EC, that you, or EC minus EF on the n side, that you know if you know the doping. Then you go again this much, which is phi n, okay, you reach this point, right. Then you come back here, which is minus delta EC, then you go up this point, which is this quantity, that is the band bending. Then you come back fully the band gap of the p side, then again you go up by this quantity, which is EF minus EV, and you come back again the Fermi level. You understand my point? I am starting from the Fermi level, I am doing one circle, essentially one motion around the band diagram, and I am coming back again to the Fermi circle, this thing. So, I will use another slide and I will show you what I am talking about actually. You remember that this quantity plus this quantity is actually the total built in voltage, but you can also derive it in the same thing. You can actually find these values in a function as a function of band gaps and all. So what I was telling you is that, you know, I have a Fermi level here, for example. This is your Fermi level, and if I look at the band diagram there, it looks like this, right. Then it has like this, and this, right. Sorry, this is a little bit not so correct. Okay. Okay. So this is the band gap on the p side. I'll call it Eg in small p. That's okay. So you see, if I start from this Fermi level, this point, suppose I go up by this quantity. What is that quantity? That is Ec minus Ef on the n side, right. So that is Ec minus Ef on the n side, which is very easy to find out if you know the doping, by the way, Maxwell-Boltzmann. Okay. Then I start from this point and then I go up by this band bending. This is the band bending, no. If I go up by band, that is phi n. So plus phi n, that is the band bending. I reach this point now. I come down by this quantity, which is delta Ec, right. So minus delta Ec, that is the discontinuity. Then I again go up by this quantity, which is your band bending on the p side. This is called phi p, that I wrote the expression in the previous slide. So I'll again go up by plus phi p. Then I reach this point and I come back the full band gap of the p side. So minus Egp. I come here, I reach this point, I again go up by this quantity, which is plus Ef minus Ev on the p side. Then I reach the Fermi level only, no. So I started from here, I reached here. So the total equation has to be 0. So your built-in potential is actually this quantity plus this quantity. So that built-in potential will be equal to, you can take the other things other side, delta Ec plus that is this plus this whole band gap, the entire band gap, I mean Egp, minus this quantity and this quantity. Okay, I can call it as like, you know, psi n minus psi p. This is this quantity and this quantity, which is easy to find out, that is Kt by Q ln of Nc by Nd on the n side, similarly Nv by Nd on the Na on the other side. So this is very easy to understand. So this quantity will also give you the built-in potential, which I had told you in the previous slide is essentially this quantity plus this quantity. Okay, that is the built-in. Now this is only one type of heterojunction, by the way. There could be many other types of heterojunction, you know, heterojunctions that where depletion approximations actually break down. There can be many types of heterojunctions. So for example, if I talk about heterojunction where, you know, I have suppose I have a vacuum level. So I'll use the black color for the vacuum level. Suppose this is the vacuum level, EVAC, and suppose I have a narrow bandgap semiconductor here. I'll use the blue color probably, a narrow bandgap semiconductor here, EC and EV. There is a narrow bandgap semiconductor. It's lightly p-type doped here, and on the other side I have a wide bandgap semiconductor EC, and then I have EV, and this is very highly doped. So the Fermi level is almost touching the conduction band, which means on the n side you are not going to get any depletion. For example, you are not going to get any depletion on the n side. Then how will the band diagram look here now? So essentially your entire depletion will be on this side, right. So essentially your p-type semiconductor will bend in order to make the Fermi levels align. So this Fermi level has to align with that, right. So what will happen is that the p-type semiconductor will move up, this whole thing will move up essentially to align the band. So and far away from the junction it has to be the same, and you should keep in mind that at the junction, you know, at the junction you should actually fix this point, which is this point and this point. So this conduction band will actually get fixed here, but it will move up like that. Okay, this is conduction band, and your Fermi level has to align, right, and the valence band also has to, this point will fix up. Okay, this point will fix up and it will go away. So eventually your Fermi level has to align, and far away from the Fermi level will align like this. You see this side will have no depletion because this is very highly doped, right. There will be no depletion here, by the way. Okay, so this is the Fermi level eventually, that is the global Fermi level that will form here, and this point was the valence band of the semiconductor. Far away from the junction it has to be same, so it goes like this. Okay, the band gap has to be same everywhere on the left side. So anyways, so you know you, okay, so it, sorry, so okay, so it has to go like that. Okay, it has to go like that. The band gap is same of course everywhere. Far away from the junction, this point has to be this spacing EC minus EF minus EV has to be constant, and there is a huge depletion here. You can see the whole band gap. It's actually inversion that is forming here. You can say, you see, remember the inversion in silicon MOSFET, same thing is happening here actually in a way. Okay, and then you will have this delta EV like this. Okay, it will not bend so much, this will not bend, and this will form like this, and this is Fermi level that is going above the conduction band. You see this conduction band, this is the conduction band, this conduction band is going below the Fermi level here, this is the Fermi level, which means this part has a very high density of what we call 2D electron gas, just like your silicon MOSFET, except that there is no SiO2 silicon dielectric constant here, but it's only semiconductor on both sides, but the bands have bands so much that there is an inversion here. This is a p-type semiconductor because this is the Fermi level here. Instead, in the p-type semiconductor at the interface, you are getting a very high density of electron gas. It's actually and a very high density of electron gas, it's inverting actually, you know. So there are different kinds of heterostructures you can form depending on the band diagram, the band alignment, the electron affinity, and the band gap. You see, because there is a very high density of electron gas, this is highly conducting. So in this junction, your depletion approximation cannot hold true. Okay, depletion approximation that we use in our conventional PN junction does not hold true in this case. Okay, does not hold true. Okay, you can see that the depletion approximation cannot hold true because in the junction you have a very high density of electron gas. This high density of electron gas makes sure that although this is depleted, you have very high conductivity here. So the whole thing is not depleted. That's why your depletion approximation breaks down, and in such cases you also cannot apply your classical Maxwell-Boltzmann approximation cannot be applied because this is high density. You have to use something called jurisdiction that I had mentioned to you long back, if you remember, jurisdiction. So there's many kind of things that you have to, you know, take into account when you draw heterojunctions. There can be many types of heterojunctions, you know, depending on the alignment. You can have an inversion, you can have accumulation, and so on. So there's this kind of things, right? And these are used actually in practical devices, by the way. I'll tell you about the devices very soon. I'll tell you about the devices, what kind of devices can be made, and I already told you that particularly in a well box can be made. LEDs and other things are definitely taking advantage of such heterostructures, but in a transistor also you will see a lot of actually applications that use this kind of heterostructures. Okay, and now and the next we will start next time is called the graded heterojunction. Graded junction. Graded junction as in the band gap is graded actually. You can change the band gap as you go over the position. Okay, I'll tell you how to do that because, you know, if you are having gallium arsenide which is 1.4 electron volt, and you have suppose having aluminum arsenide which is 2.2 electron volt, you can either make a heterojunction like gallium arsenide, aluminum gallium arsenide. So the heterojunction will look something like, you know, like this, of course, like this, but you can increasingly grade it. You can, as you grow the material, you can linearly change or exponentially change the band gap of the material, and that's the beauty. You can actually use that, and that is routinely used in your devices like HBTs that are actually used in your cell phones, by the way. So this is not something fancy, this is actually practically used in the cell phones and stuff. Okay, so let us wrap the class here today for this lecture. We have talked about heterojunctions and heterostructures. We introduced the band diagram concept, PN junction and other things, how the band alignments are there. I hope you are now familiar with heterojunction band diagrams. There can be different alignments, different dopings, different band gaps and band alignments. So depending on that, you have to think and draw the band diagram. It can be PP, it can be NN, NP, PN, and wide and narrow. They can have different combinations, and you remember the straddling, staggered, and the broken gap alignments depending on the electron affinity. So when you are given a new heterojunction to make on both sides, you just do that thing. You see, if both are doped moderately, then depletion will be on both sides. So depletion matlab your Fermi level and the conduction band, or Fermi level and the valence band, depending on N on P, N or P, will increase. That gap will increase, but far away from the junction, it will not be any influence. Okay, that you remember. And secondly, you draw a hypothetical line, vertical line. You fix the points where the conduction and valence bands are supposed to be there, and hooking that, you know, clutching that to that point, you shift the band up or down, and let the Fermi level move up and down so that the Fermi level becomes aligned everywhere. There is no step in Fermi function, right? And those points where you fix the conduction and valence bands should be in position, and you join those edges eventually. You will get a delta EC, delta EV. That the discontinuity is a band diagram. Okay. Any questions, you can always email me, chat with me, you know, for this heterojunction band diagram. It's very important because the devices based on heterojunctions are very exciting, because you have a lot more things to do, and a lot of research is going on those things. Okay. So in the next class we'll start with graded heterojunction, which will be advantageous in many applications that you will see. Okay. So, we will end the class here. Thank you for your time.